Welcome to the From Scratch podcast, everyone. Today we're joined by Thomas Ball, a visionary at Microsoft Research with over 25 years of experience revolutionizing computer science education. From the BBC Microbit to device script, Tom's made coding accessible and exciting for kids worldwide. With 40% of US students struggling to read and STEM scores at their lowest since 1995. Tools like the Microbit, launched in 2015, are pretty vital, turning learning into a hands-on adventure. Yet, education continues to face pretty big challenges. Today, 250 million kids are out of school globally, and by 2030, 65% of today's students will work in jobs that don't exist yet. So the question is, how do we prepare them for an AI-driven future? And that's gonna be basically what we're gonna be exploring today. Tom, with you, we'll trace through your journey from microbit to device script, then just tackle AI, gamification, global education gaps, and just the art of teaching kids to think really creatively. So, whether you're an educator, a parent, a tech fan, you'll love this. And yeah, Tom, it's really, really great to have you.
Yeah, thank you so much. It's great to be here.
Cool. So what we kind of want to start with is first, can you kind of just give us a quick rundown of what your journey was like before the BBC Microbit came along in 2015 and kind of what got you passionate about coding and education and how did that lead to this kind of game-changing project?
Sure. Well, I cut my teeth on the Apple II back in the early 80s, where you really learn things bottom up by learning sort of the guts of the computer and how to program it at a low level. And at that time that we had the Apple II in the United States, there was something called the BBC Micro in the UK, which was a similar sort of computer. It was based on the 6502 microprocessor, just like the Apple II was. But it also was a project that was, the BBC was quite involved in terms of educating people in the early 80s about what a personal computer was, because the concept back then, was completely brand new. So really, my journey started with, microcontrollers, like the really early ones, the Apple II. My Apple II had can't remember, K of RAM, external floppy disk drives. I had what was it, a 1200 baud modem. That was like big deal back then. Anyway, I got really into games and programming games. So I programmed some games with a friend back in high school, and we sold them. At the time, we sold like 10,000 units of this game called Falcons. So in the early days, I got really caught up into graphics and gaming, and then I sort of found my way to really getting interested in programming languages and compilers, and sort of how do you actually program, and what are all the different ways you can program. There's functional programming languages, imperative programming languages, object oriented. There's things like Prolog, which is a classic staple of AI, of classic symbolic AI. And so, learning about programming languages and foundations, programming languages are a way that we humans communicate with the computer, right, at a higher level of abstraction, and we can sort of tell it what to do. And learning about all the different ways in which hardware and software come together was really fascinating to me. So that was sort of how I got into research in programming languages and program analysis. And really, ever since I finished my PhD in 93, I've been in an industrial research lab. So I was at Bell Labs for 6 years. And then since 1999, I've been at Microsoft Research as a researcher.
So I'm really curious, how did you get into the education intersection of this? I mean, you were working on kind of hardcore research before and working on compilers and static analysis, but now you've kind of made this journey over to working with education specifically. What was kind of your motivation for that?
Right. So it actually came, a lot of great research is all around sharing of ideas and what I call Brownian motion. Somebody has an idea over here, bumps into somebody else. A lot of research is sort of bottom up. Like, we don't necessarily know where we're going. We have an idea, but we have all these particles bumping into each other. So we had a fellow in our group, Nikolai Tillman, at the time that Windows Phone came out. And you may remember Windows Phone and the Metro interface. It was a pretty nice product, but it was, it was third in the market. Yeah, it had its day, but that day is gone. But at that time, if you wanted to program like a Windows Phone app, you needed a big desktop and you needed to download Visual Studio. And, when you compare that to how a lot of us programmed our original computers, you programmed the computer you had on the computer. You didn't need a separate computer to program it. So Nikolai came up with this idea of touch develop. What if you could use the touch interface? I don't have my phone here, but you get the idea. Yeah, I have a phone and it has a touch interface, but I want to program the thing, and I don't have a keyboard. So touch develop was an app that allowed you to program apps for the phone on the phone, which is like a supernatural thing. And it was really born out of this idea of the hobbyist computer, right? That is, you get a computer, well, that computer is programmable. So why can't you program that computer on the same computer? And as we got into that, another member of our team, Peli Dehelu, was like, wow, I volunteer in the Seattle school system from a program called TEALS. So TEALS was a way to partner people in tech with teachers who wanted to teach AP computer science. And so the tech person would come in and teach the class, and the teacher would learn. And Peli was doing that. He said, look, touch develops super. Like, if we get a gift of Windows phones, we can go into the school and we can show the kids that these phones that are becoming all the rage are actually programmable. Like, you can actually do something with them. So really, we started this research project, which was, can we take ideas from programming languages and human-computer interaction and use them to make it possible to program the phone on the phone, touch develop. And then we started doing trials in schools, and we had something called app days, where we had like a whole afternoon where the kids would come in and there were prizes and contests and for the programming. And Peli really drove that. So as a result, Microsoft was like, oh, you guys are doing, we have learning education resources. Let's create a course around touch develop. And so that was like we sort of backed into it. We are software engineering researchers and programming language researchers, but through Peli and his boots on the ground approach with the schools, we started saying, look, there's really goodness in making it just easier, like reducing the friction to programming, and also saying, hey, this consumer device, which you think is so cool, you can actually control it. You can learn about it. And to me, that's like a fundamental aspect as we go into the world of AI, that all the stuff we're doing is built on computers that people have built. And we should understand at least what this mechanism is. I mean, we learn about the combustion engine, we learn physics, we learn all these things. And, I feel it's important to sort of understand things a little bit bottom up, like these foundations. So this is how we sort of got into it. We got into it through touch develop. So any questions about that? I can keep talking, so I want to make sure I give you guys time.
Yeah. I mean, I have a lot of questions, but honestly, just at a high level, for people who might not have like used touch develop or like kind of any of these people who haven't even gotten into programming, could you kind of describe like the stack sort of? So like you have this device, you might be able to just click and drag things, move them around, even like
Yeah.
before we get into microbit, just a high level overview for someone who might not be familiar.
Yeah. So when we think about programming languages, I mean, often people think about people typing on the keyboard, and then there's errors and things go wrong. And with touch develop and other beginning programming environments, we use sort of a drag and drop approach where any program you create is correct by construction, right? Will it do what you want? We don't know, but any program you create is runnable. So the first thing, and there are various systems that use this approach, is to simplify the user interface from sort of text-based coding to sort of more of a drag and drop but paradigm, where you can select, sort of like Lego blocks, you can select these blocks and put them together, and then they do something. And one of the ways then you learn is by just putting the blocks together or the pieces of code together, and the program runs and you can see what it does. So you can sort of learn through doing an exploration, and you don't necessarily need to worry about about errors, right, that are sort of not understandable, like a syntax error. What's that? Yeah. So touch develop and a number of other platforms, you've probably heard of Scratch and then MakeCode as well. They use something called Blockly, which is an open source framework from Google, which allows you to do this Lego sort of construction of a program, where every program you create has some meaning, right? It will run. There are no errors, essentially.
Yeah, and So yeah, this kind of brings me back to when I was a kid, because I remember when I was in middle school, I think we did a little bit of Scratch development, and I remember that was kind of like our initial intro, and I thought that was a pretty interesting concept. I don't remember, I think it might have been, I don't remember what the program was that we were doing, but definitely it was like we had Bill Gates and a bunch of really famous people explaining like how Scratch
Yeah,
worked, and
yeah.
so like
That
there
was
was.
that was code.org.
Yeah, yeah, yeah. I think that's what it was. Yeah, yeah. So I'm curious because from a programming perspective, you guys are taking the approach of like also integrating like the hardware, right? So before we get into like the microbit, you guys also bring this hardware component kind of to the picture. What's kind of the reason for that? Like, why do you think it's important to have hardware that runs code versus just having like, the click and drag and drop interface kind of for kids to play with? Do you find that the hardware is more engaging and more informative for the students?
Well, yeah, I mean, if you think about the number of computers that exist in the world, the ones that we actually interact with as humans, like laptops and desktops, are just like such a small percentage of all the computers that are running everything in the world, from our economic systems to transportation. And so computers like the microbit, which I have here, are embeddable. And I think it's super important that everybody sort of understands that all the systems that we have are running not just because of people, but because of embedded computers that are sort of invisible behind the scenes. The other aspect, so that's one aspect is to say, look, there aren't just computers that you use. There are computers all around. There are computers in your car controlling the speed, anti-lock braking, like all those things that you depend on for safety. The airbag system, there's a computer running that thing. And so the other aspect is that this whole notion of physical computing is the idea that because the devices are small and embeddable, you can actually, put them into projects. Like you can create a robot. Like what's a robot but a number of computers with servos, right? And so this idea really that the world is based of all these systems we create and that computers are embedded in them is pretty central. I think pretty key for people to understand. And also because physical computing, kids like to run around. So the other idea is like with the microbit, you can like create a step counter or, and you can attach it to your wrist and then you can like go run around with your friends and then see how many steps you got. So there's also this idea that, that computers are actually just not these abstractions that serve up web pages, but they're actual physical things that you can put on your body. You can take out and you can measure the weather. You can embed a computer in a case and then measure precipitation and temperature, over a whole semester, say. So I think this idea is fairly critical. I think we've done a great job in the computer industry of having all these layers of abstraction where we sort of hide the guts of the computer and we wrap them up either in cell phones or tablets or desktops, laptops, or hide them away in the cloud. But I think with the microbit and other sort of devices like the Arduino, you really get to understand that the computer is this very tiny gadget that's programmable, but also embeddable. And then with sensors and actuators, it actually can affect things in the real world. Like it can break, it can control your car. It can make a transaction. It can save your life. A pacemaker, for example. So I think it goes beyond, in my mind, the great abstraction we have of the screen and the mouse and everything we have with, you know, gaming, which is fairly abstract when you think about it. Physical computing then is this idea that computers are actually interacting with the real world and sensing and reacting to that. And I think that's going to be like tremendously important as AI really makes robotics and so much more possible. I think we're just at the tip of the iceberg here with the LLMs. If you've been tracking, like the world of robotics is completely transforming, and we're going to have these robots that we are working with or that are working for us or that we are working for. And so I think it's even more critical that we understand that computers aren't just this cool thing for games. They're really everywhere in the world. They're in all our systems, and it's just going to increase because of Moore's law, because of the because of the essentially low cost of this incredible computing power, plus storage, plus networking.
And one question I had is, so what was it about this drag and drop kind of like paradigm that made y'all realize that like this is the level of abstraction that kids can operate at, so that they later can become good at the lower level programming. Like is that kind
Well,
of the
that's
whole goal of it?
well, I don't know that we have the evidence that says it. If you start with scratch, you're going to get a conceptual model that are Blockly that helps you with the lower level programming. I'm not sure about that. I mean, the main thing I see with Scratch is that in the Blockly paradigm is that it welcomes more people who might be just turned off by compiler error messages. It allows exploration and interactivity in a sort of a safe sandbox, right? Now that said, yeah, one of the things we're doing with MakeCode that's quite different and with the microbit is like this thing, there's no operating system running on it. There's no levels of abstraction like we have in the browser, like we can download JavaScript frameworks. So what we've done, and what we did with the microbit project was we created a web app plus Blockly that embeds Blockly and allows you to code the microbit inside the web app, first using a simulator. So we have a simulator for the microbit, which is an on-screen depiction of the microbit and most of its functionality. So you can use the drag and drop paradigm, code it and simulate, see the simulator. And then what we have is we have in the browser a full compiler all the way from the blocks down to TypeScript, down to essentially ARM assembly, with the ARM Cortex M4 is what's on the microbit, and then to machine language. And we link that machine language, which is all compiled in the browser, because we're compiler guys, so we just did it all in TypeScript. We compile everything to different representations. We then link the compiled user program against a pre-compiled C++ library, and you get a file that you drag and drop to your microbit. So you were talking about, yeah, so we have like all these layers that we can expose. So at first, it's super easy to program the microbit. You use the blocks. But if you want to go on and go further, we have text-based coding. So one of the differentiators between MakeCode and, say, Scratch is that we allow you to switch from blocks essentially to JavaScript, code in JavaScript, and you can actually go back to blocks. You can go back and forth. But I think your bigger question is interesting. Like, is Scratch just a nice way for people to get an introduction? And then, how many people does it help, like, get the coding bug and then go on? That's an interesting question. I don't know. I don't know that we have good data on that. But certainly part of the goal is to attract more people into computer science, into programming, and showing them that, that there are sort of different levels of complexity to coding. We have these high-level programming environments that make it super easy with a lot of built-in behavior. And then as you want to get more control, you sort of have to go lower level. So with MakeCode, we do try to do that. In fact, MakeCode does get, and the microbit gets used at the university level as well, because they're C++. You can also code the microbit in C++. And there's a whole number of programming languages and systems that have created runtimes for the microbit. So there's actually like a huge selection of different types of languages you can code the microbit with.
Yeah, that's really awesome. I mean, I'm taking a compilers class, so a lot of this stuff is just like insane to me. Like, I don't even want to imagine the technical overhead of like having a compilation process in the browser that
Yeah.
ships onto these devices. But I'll definitely ask you more about that later because I think it's really, really interesting. But I kind of just want to go back to the initial conception of the microbit because obviously there was this BBC thing going on at the same time. You guys had this massive public initiative to get these devices to lots of people. So I would love if you could just like walk through kind of the conception of the project, kind of
Right.
what was going on at the time and like all of that. Yeah.
Sure. So the BBC really drove that. They did like 2 years of research while we were doing Touch Develop. They had been thinking about the BBC Micro, the personal computer, and they wanted to do something that was closer to an IoT device. And so they were inspired by things like Arduino. They had studied the use of Arduino in the classroom, and they worked with some professors, I think, at I can't remember exactly where. Maybe it was Manchester, but they worked with a bunch of researchers even before we got involved to really do a prototype. And there were two main ideas there, probably more. But the first idea was that the microbit, or whatever it was called at the time, it should have a bunch of things built into the board. So with Arduino, for example, like you basically get the microcontroller and a bunch of headers. And then if you want to do anything like light up an LED, you have to wire it, which is cool. I mean, on the other hand, for teachers, it's just one more thing to clean up. So I think part of the idea of the microbit is that, it's got a 5x5 LED matrix. It's got buttons. It's got an accelerometer. It's got a speaker. It's got a microphone. So like out of the box, there's a whole set of things you can do with it without doing any wiring, any extra wiring. And I think that's sort of a big differentiator from zero to hero, like, and also for the teacher, it's all in one, right? There's no extra things you need to do. The other aspect that they prototyped was using Blockly. Yeah, they wanted to have, a drag and drop interface. And what they did was on the client side, they compiled the blocks to C++, and they sent it into the cloud to a compiler in the cloud. This is the user program, and they would get back the binary. And so that was the start of what they did. And in 2015, they wanted to make it real. So they put out a request for participation. And at that time, we had been doing Touch Develop. We had been in the classroom. We had started working with some hardware. And so I led a team and we made this big proposal. We said, look, we have this whole web-based programming stack. We know about Blockly. We hadn't used Blockly, but we were doing similar things. And, we'd love to participate. So we made that proposal. And there were many other technical partners that came in. And then there were partners that did content and training. And there were other partners who provided funding. So it was purely from the BBC. It was a philanthropic effort headed by the BBC. And the goal was to bring to every year 7 student, that's like a 5th grader, I think, a microbit. And so in the UK. So this is about like 800,000 students. And so it's a pretty big drop with, again, the BBC providing a lot of educational material, but as well, all these partners helping. So Microsoft, we were part of the core technical team, and we really worked on the programming environment, which initially was based on Touch Develop. And Touch Develop, you might think, oh, wasn't that a phone thing? No, we had migrated it to a web app. Because as I mentioned, Windows Phone didn't do maybe so well in the market. So we said, look, there are all these other things like tablets and laptops that have touch. Let's re-architect from a Windows Phone app to a web app that's still touch-based, that still has the friendly user interface like Blockly. Yeah, so the BBC, it was really their vision, which was really cool. But, as we got into it, what we did is we started doing user trials. Like we would go into schools and we basically started with our initial prototype of copying their architecture. And what we found was like schools' internet connections were going up and down. And like every time a student edited a program and wanted to compile it, it had to go to the cloud. And, the compiler service was up and down, and then the internet connections were up and down. So basically the fellow we called the wizard, Miha Moskal on our team said, look, I'm just going to do it all in the web browser. As soon as the whole web app is loaded, you're done and dusted. That web app is resident. Even if you come back and you don't have an internet connection, it will still work. So we put the whole compiler, for the user code into the web app. Now we still needed a C++ compiler for the runtime, but that's fixed. So that blob would also be part of the web app. And yeah, so the BBC started with the vision, but then to make it real, they needed a whole set of technical partners, designing the hardware, doing the firmware. And the C++ runtime was done by Lancaster University. We did the web stack essentially, and we were responsible for the original website.
I mean, that's awesome.
It was crazy. And when we had to deliver this thing on time, it was very visible. It was visible in the UK. It was visible at high levels in Microsoft in the management. So yeah, it was maybe one of the riskier things I've ever done in terms of public, in terms of the stuff I had done before was tools for professional developers. Now there's a bug there, file a bug for you. But yeah, with the microbit, it was a whole different level. So yeah, it was super exciting. And the BBC had a great vision, but they needed a set of technical partners as well as all these other partners to really pull it off.
Yeah, I think that's a really understated feat for people who might not be sure of what's going on. I mean, moving the compiler completely into the web browser just so that someone can load it up.
Yeah, it's amazing to have people on your team like that who are just like, yeah, I've written 10 compilers in my life. It's just another compiler.
I mean, just kind of getting into that, why I think it's a crazy feat as well is the laptops that the kids have access to as well. They're not the craziest laptops either. So How did you guys do it? Like, you're juggling all these performance considerations. You have the laptop with the web
Yeah.
browser to load it, and then obviously you have the microbit itself, which isn't, this big device with a lot of compute. So how did you guys do these performance considerations?
So, I mean, it was really driven by the schools. We're basically like, okay, we're sitting here in Redmond with these powerful laptops and desktops. That's not the reality. So this is a web app. It has to work, across Chromebooks. It has to work across tablets. It has to work across all these different types. So yeah, we collected a lot of different hardware, and we also like surveyed like what's out there in the school system, right? And making a web app that works just across low end laptops to give you decent performance. Yeah, a lot of performance tuning. Also, we actually made it mobile friendly. So you want to make it, I mean, with the laptop and desktop, it's mouse. With the tablet, it's touch. Then we actually are embedded inside phone apps. So that coming back full circle to touch develop, BBC has a iOS and Android app that embed MakeCode inside a web view. So like we have to be mobile friendly in terms of layout. So a huge amount of work. I mean, just a huge amount of work of the team, but really driven initially by the microbit in the UK, and really, really the idea is, yeah, we need to make this thing performant. And yeah, so I mean, a tremendous amount of work. Obviously, we had the experience of doing touch develop as a web app, so we weren't coming, we weren't starting from scratch. We had a lot of ideas about how to make things more efficient. But yeah, there was tremendous amount of engineering, and even to this day, just to keep up with web standards. For example, Web USB came online. I don't know when it was announced, but maybe 6 years ago. But initially it wasn't great. It's gotten better. Flashing the microbit over Web USB when it works is so much better. Like kids these days, they don't know what a file system is, right? You ask them to navigate to the downloads directory and copy this hex file that the browser created, over to this other directory, and they're like, "What's a directory?" And seriously, I mean, and why should we be surprised? So Web USB, for example, is another thing that we've been on top of in order to, make it easier to flash the microbit. Yeah, so yeah, tremendous amount of work there by many, and a lot of testing.
Yeah, and the second part of my question was kind of like, and I'll add on to this a little bit too. Like, we've been talking a lot about abstraction, like sort of the key components of abstraction as well. As you guys were trialing this, kind of like going into the classes and then like having like the kids work on it, what were some of the things that you guys were like getting back in terms of feedback? Like, what were the things that you guys learned just from that experience? Obviously, you guys learned about like the internet connectivity and the importance of embedding the compiler into the web app, but like, what were some of the other things that you guys like noticed and observed?
Yeah. Well, I mean, there's a whole question. Just because we have Blockly doesn't mean it just means we have this drag and drop, but we have to design the APIs, right? And Peli did a huge amount. Peli de Helou did a huge amount, and we did a huge amount of iteration on the on the blocks. Like, what's the actual syntax? What's the wording of the blocks? How do they work? And we iterated a lot, and we still iterate to this day with the Microbit Educational Foundation. Anytime we introduce a new block, we go into the schools, we trial it, we sort of understand, what's working, what's points of confusion, where things need to be reworded. Yeah, so one of the things that we did that I think has worked out well is to make it very simple to do reactive programs. So, in classic sort of like Arduino or sketches, you would do a lot of polling. Like you create a loop, and this is what I consider like more low level coding, right? You'd create a loop, and then you'd say, okay, every so many milliseconds, I'm going to like poll the accelerometer and do something like that. But that's what I call already low level coding. So where you need variables, instead, we took, as in Scratch and other things, an event-based approach. So essentially we said, look, if the accelerometer shakes, we have an event for that. So we have an event handler block where you can drag a block in and say, when the A button is pressed, when the accelerometer moves, then do something. So we made it super simple. And that really worked out well to do these reactive programs where you only need two blocks. Like you need a block that says when the A button on the microbit is pressed, then draw something like draw a heart or some other image on the 5x5 microbit screen. So yeah, so we definitely had done that style of programming as well in Touch Develop, because we developed a game engine in Touch Develop. So, and we did get a lot of feedback, about that. So when you do event handlers, well, what if you have an event handler for button A, an event handler, and then you drag another event handler for button A? How should those things compose? And we saw that people were really confused. So like in MakeCode right now, when you program in blocks, you only get one event handler for each event, right? And the other one gets disabled. So there were a lot of, like, once you make a design decision, there are all these consequences, and some of them foreseen, some of them unforeseen. So, we definitely, in the blocks, we limited the type of programming you could do. Whereas when you go into JavaScript, it's more freeform. You can register multiple event handlers. There's just like a lot more complexity. So that's another thing about like the whole experience. Like the programming experience that you have in blocks is limited. Like you can't write any program. There's limitations. And part of that was just learned by iterating with the students. Yeah.
What were some of the abstractions that, I don't know, like if you might be able to answer this, but what were some of the abstractions that you guys kind of had to change so that the kids could write the programs like in an easier, more intuitive fashion? Because I mean, you mentioned this earlier, like, some of these kids, they don't have the technical know-how of like the directory and all this stuff. So making the coding more accessible, like what was the thought process like in terms of like, okay, how do we make these blocks intuitive so that even the kids, can kind of understand what's going on?
Yeah, well, I mean, we had a lot to go on, and we had, obviously Scratch had done a lot of work. We learned a lot from that. I mean, one thing is to encapsulate, like, to have blocks that are big step, that do a lot of things for you, right? And then if you want to like break it down, you can go to lower level coding. So one example is, we want to read a value. We want to read a value from the accelerometer or from the temperature sensor, and we want to, scroll it across the screen, right? The value might be 3 digits, so it doesn't fit. So, we provided like, abstractions, for basically scrolling a text across the microbit screen. We thought about, and we worked with teachers, like what are a lot of the lessons you would want to do, and we made sure, that to get started, you would have like these higher level primitives that, you wouldn't have to like implement your own display driver. I mean, obviously, like we allow you to, like, as a programmer, plot every element of the 5x5 matrix independently. Like you can go down to the low level and you can have complete control over the screen. But think about the program you would have to write, right? So again, it's about layering. I don't think there are any really big surprises for a lot of the things. It's about layering and having these higher level abstractions. One of the ones that really, really makes the microbit sing is the radio. So microbit has a Bluetooth antenna, Bluetooth low energy, but it has an underlying stack that lets us essentially just do broadcasts. So you don't pair, you just send messages out. And we made it super simple to just like send a message on the radio and receive a message. Again, sort of event handling, so that this basic piece of hardware is accessible. So sort of every piece of hardware on the microbit, we have some higher level abstraction that makes it really easy to work with that. And then if you want to go down to the pin level, if you want to do GPIO, we have all those APIs too, right? But basically there's all this stuff going on to really, read off the I to C bus, all that stuff. We hide, as many environments do. We hide that in layers of abstraction. But basically, we want kids to be able to do programs that are interactive very quickly. So we also have like a whole library of sounds, of existing icons, but some of the kids really get into programming their own animations. So, you can actually create a sequence of frames, animation frames, and then just control control completely explicitly what's going to appear on the screen at every time step. Yeah. So I would say there's a lot of layers, and we sort of have we sort of have the higher level ones up top, and then we have the advanced layers down low. And there's a lot that one can do beginning programs just with the higher level abstractions.
Kind of building on that, what were some of the coolest things that you observed that like kids were building? We read into some stuff where kids were getting involved in like mini robotics with like Lego Mindstorm robots, and there's some really cool stuff that people were doing like
Yeah,
with
I
the
mean, there's a ton
platforms
of
that.
stuff. There's a ton of stuff. It really depends, not just on the kids, but on the teachers and all the people who've invented like lots of yeah. There's this great book that I just happen to have here by Pauline Moss and Peter Heldens. They're both teachers, and yeah, a lot of the cool stuff is like that we started out with. It's like you build your cardboard robot. Like so, you build a robot out of cardboard with the microbit sort of on its face. And then you can have the microbit. It turns out LEDs are not just light emitting diodes, they can be used to do light detection as well. And so one of the cool things was to create your own robot and then have the microbit detect when the light level goes up. So you shine a flashlight or a phone light at it, and then have the microbit like open and close the robot jaws using a servo. So a lot of the cool projects were about embedding the microbit. Super simple program that's super popular is rock, paper, scissors. So you shake the microbit, you throw a random three-sided dice, and then based on that, the microbit shows either rock, paper, or scissors. And then you can play by yourself or you can play with somebody else where you're using the microbit to do the choice. All right. Yeah. So, there's been so many fun ones. There have been a lot of partners who, at the time, there was I can't remember the name of the race car, but there was a jet propelled race car in the UK. And the fellow and his organization said, oh, that'd be cool if you had a little race car for the microbit. So what happened was the kids created their own model rocket cars with and they'd run them on a track on a wire. And then the microbit would get embedded, would slot inside the car and it would measure the acceleration in 3 dimensions. Right. And then afterwards, and this was done in partnership with Microsoft, there's a whole team to essentially really get the kids interested in creating their own car, but then measuring its performance in terms of like, oh, is your car lifting off the ground? And so the idea was they would do these runs with their car. The microbit would collect the data via a program, and then they would bring it back to the computer and they would look at the data, and then they would go back and try to fix their car. So like if you think of like Formula One or Indy, whatever. This is what people are doing professionally. They've got systems. They're heavily instrumented, and what this project was taking the kids through the whole mechanical engineering, building the car, racing the car, and then also getting the instrumentation. So that was a really cool project.
It's very interesting because you guys kind of had to balance this issue of like, we want to make something that's extremely like performant and general purpose so that the kids can kind of create all these applications, but then at the same time, you guys needed to make sure that, the system was kind of closed. You can't just make any program like you were saying before.
Although once you go into the TypeScript, you get a lot more freedom, but still there's an abstraction of our operating system, if you will, at the bottom.
Yeah, yeah. And so I guess just kind of like looking at the bigger pictures. So you guys have the microbit, you guys have MakeCode, which kind of becomes this bigger platform where you guys can kind of do just general purpose programming for not just the microbit, but it seems like there's other hardware that also gets integrated into the MakeCode platform. You
Yeah,
guys made MakeCode Arcade. So you guys started like kind of branching out now, and
right.
is this there's this really really cool hopefully I can like I have the video playing over the podcast, but like these devices like really look really really cool, and so now people are working on, or like I guess kids would be working on these games. So can you kind
Right.
of walk through like MakeCode Arcade, the
Yeah,
differences
so
and approach for that as well?
right. So one of the things we did so MakeCode got started because of the success of the microbit in the UK, and we got support from management and my team, myself, Mihal Moskal, and Pele Dehalu. We went and helped form the MakeCode team and developer division back in the fall of 2016, and that team is completely independent now. We sort of showed them what we did. We worked. But what we did was we moved away from Touch Develop. We mothballed Touch Develop because it was like developed back in the day when there weren't many JavaScript frameworks. And, we wanted to do a more modern framework. So we created, Pele and Mihal primarily created something called PXT, the Programming Experience Toolkit. And the idea was, hey, we want to rebuild the editor for the microbit. We want to include Blockly, and we want to have it work with JavaScript, TypeScript as well, and have this multimodal aspect, which we didn't have before. So we had lots of ideas, and we didn't want to just make one editor for the microbit. We said, look, there's lots of different types of physical computing. Let me just find another one. Yeah. So at that time, we're like, look, there's like Adafruit, and Adafruit has this awesome thing called people call this the square board and then the round board. So we like, hey, what about the round board? And the round board, it like has neopixels and all that stuff. So we went sort of wild, and we said, look, we have this new framework. We can stand up editors for like not just the microbit, for other people and other companies that are doing physical computing for education. And Adafruit was like our second editor. And you can find those if you go to makecode.com at the bottom of the page. But what happened over time was we realized, look, every time we have a new type of hardware, it gets more difficult. We have more editors. Really, our management chain in DevDiv, Julia Lewison, who's the president of DevDiv, she said, look, this is not sustainable. And she was really right. Like we had at some point 6 editors, right? And so really the message was, look, you can really only sustain so many editors. So we have the microbit, and that's going great. I mean, we've since 2016, it was turned into a nonprofit. 10 million microbits sold around the world. Yeah, MakeCode for the microbit. And then if you remember, Microsoft also purchased Minecraft. And so there was this whole idea, let's code for Minecraft. Okay, so Minecraft, very important. It's a Microsoft property now. And then we were thinking, oh, we only have one. Like, if we only have a third editor, what do we want to do? Well, we want to pack as much hardware into that as well. So what Michal Moskal did was he said, look, let's design. Well, actually, this isn't it. This is a different one. But let's think about a retro arcade device. And this is, again, like going back to our roots, like the Apple II. Let's think about a small color display, which is like 160 by 120, with with some buttons on it, and now you have sort of you have a little retro arcade board. And so essentially what we did for the third editor for MakeCode Arcade was we defined a hardware spec and a bunch of other things to make it easy to configure the hardware. And we said, look, we're open for business. We have this MakeCode Arcade. Anybody who creates a piece of hardware that meets the spec and that passes our testing, we'll add to our page. So we have the single editor, but we have many different boards. So like we have this guy from Kutronics, we have this guy from BrainPad, and then the other thing that happened was when the microbit went from the V1, which only had 16K of RAM, to the V2, which has 128, we said, oh, this thing could be an arcade device, except it doesn't quite have the screen. So that thing is a MakeCode Arcade device. So yeah, so essentially, long story short, we basically used MakeCode Arcade to do a couple of things. One is to really increase the bandwidth that you could have with the device, because the microbit 5x5, and retro arcade games, huge community, lots of interesting types of games. And we essentially said, look, at a minimum of 96K of RAM and this speed processor, we can actually drive the display and get enough frames per second. And so we now have, I don't know how many boards are on that. We have at least, I would say, 15 arcade devices available commercially. Most of the use of arcade actually is in the web browser, because again, we have a simulator, but that's super cool. So you can iterate really quickly. But I tell you, the kids love seeing their game, on a device. And that's awesome. We also have actually an Xbox app that once you create a game in MakeCode Arcade, you can export it and then load it into this Xbox app and play your game on your Xbox. So gaming is huge. And we started out, essentially thinking about it from the hardware perspective and thinking about really limiting, instead of making use of the full screen of a laptop or desktop, we were like, no, let's keep it retro so we can fit it all onto the device. So this actually took a lot more engineering than with the microbit, because now we had to support multiple microcontrollers, multiple displays, multiple types of inputs. And so it really extended the MakeCode framework in a significant way.
Yeah, kind of building on that, you guys went kind of towards the games direction. Was there a specific reason for that? Was it just like kids love games and, maybe this is a good angle to go
for? Well,
for?
to be honest, it's because we love games and we were just we were just at that point, that we needed to have a third editor, and we're like, yeah. So it was really our initiative, but yeah, it was born out of a lot of experience that we thought, yeah, they're very appealing for a number of reasons, and also like the complexity. Like if you look at the microbit programs, they're fairly simple. You don't get much into object orientation, but like the game engine, like the whole stack that we have in the game engine and everything, it's a whole nother level of complexity. There's also this question of like what type of things is it good for teaching, and I think the game engine really, because essentially you have a screen now, and you have real time, and you have this physics simulation. There's just a lot more complexity in terms of what's possible, and kids, yeah, do amazing things with it. We also provide, lots of different extensions, libraries, if you will, for different types of games. So we have platformers, we have dungeons games, maze games. So we also like do a lot with again, we have this low level. At the low level, you can have sprites and bitmaps if you want to program with that. But we have like these higher level abstractions, to make it easy to do a platformer, for example.
I kind of want to expand on this game idea because, my mom's a teacher, and the one thing I know, like, that's a common argument across any household, even when I was growing up, was like, are games negatively or positively impacting kids like growing up? And I know with this whole thing that you guys are kind of doing, it's like the kid is technically building the game and then playing it, which is like completely different from like, oh, my mom bought me a Nintendo DS and I'm
No,
addicted
sure.
to my Nintendo DS. And I'm really just curious if you could expand on that. Like what do you think as like the new generation of kids growing up, like how should they prioritize their time? Like, is it okay to game alongside other things? What's your thoughts based on the things that you've seen and the impact that like microbit has?
Yeah, I think right now we're at a very weird time where kids need to spend more time outdoors and playing with kids. I think we've been so successful in the computer industry, and then with social networking and everything. I think we do have to, like, as parents, we have to really think about, making sure the kid, has so much time to just be bored and go outside and figure out what to do on their own. So at a high level, I think we've been like the computing industry, and now with AI, I think it's very addictive and overwhelming. I certainly noticed when I was, before I wrote games, I would just plug quarters into Space Invaders, and man, that was a lot of money just going away, and then I became like a writer of games, which I felt like, well, that's a little bit better, but I really also felt like I only have so much time of my life that I should spend doing that stuff. So like I play bass, I like to sing in choir, I like to do things with people. Part of like what we do with microbit and physical computing is really like also try to get kids working together in groups, right? And obviously project-based learning, there's a long history, and I think like that's super important. With the microbit, with the games, I think there's just so much sort of tacit or implicit knowledge kids already have. They're like, oh, I want to make a game that does that, or this. I do think there's like, again, there's just value in being able to say that game and the way things work, I can understand that, I can control it. So there's definitely value of that, of being creative, of showing off your creation. I think there's a lot of benefit to that socially. Like we have something called kiosk mode, where the teachers can download all the students' games onto one laptop or desktop, an arcade game or arcade cabinet. She can't really see there very well. Sorry. But yeah, and so show and tell, like the kids sharing their games, and that's been super. So yeah, I do think there are there's just more traps that are easy to fall into. The computing is very addictive. I saw that early on with gaming. I was sort of aware of I could spend like a whole evening just gaming, and then just, oh, what happened to the time? And I think it's good to step out of that and to really view computing critically as well. The computers are wonderful, they do wonderful things, but we also have to understand that, yeah, when things go wrong for many reasons, there can be downsides. And I think so we need to balance, the coolness of these gadgets. We need to peel back the surface and look underneath and not just say, what is this computer? What is it made of? But, who's the creator and what's their motivation for getting me to use this computer?
Yeah, it's interesting because I mean, I guess I just kind of want to get your opinions on we have AI obviously becoming a lot more prevalent everywhere, sort of universally now, and one might even say that, kids, especially nowadays with access to like, tablets and just sort of computing has won its game of getting a device into almost every person's hands. And so with that, we have these LLMs and AI sort of integrated into the apps. Kids can talk to ChatGPT, and, kind of get the answers to everything. I'm curious, like, what are your thoughts on sort of abstractions getting bigger and bigger as sort of kids go through school? Not even just kids, I mean, even in college, people who are studying computer science, for example, just relying on like ChatGPT and AIs in general for the programming aspect of it. And so the new programming language, it's kind of like a meme, but it's like English. English has become the new programming language, and then the
Yeah,
LLMs make the code. So
yeah,
as someone who works with hardware and like you sees the importance and value of hardware, like, what do you think about that transition that's happening?
yeah. I think this, we're still a long way. I mean, the level of detail you need to get things right in code is extreme. And the LLMs, there are many studies that, I just read an intro of a recent paper that basically says, unfortunately, the LLMs are only as good as what they were trained at. And they were actually trained on a lot of code that has a lot of bugs. So they keep making mistakes. And then when you show them the error of their ways, actually LLMs are worse when they're asked um, to correct mistakes. So it's not always great. So I think there's still a huge amount of complexity under the surface. The LLMs are working at the syntactic level. They appear to have some semantic knowledge, but it's pretty limited. And so if we as humans don't really understand what's going on, who's going to audit the thing and say, this code is correct? I must say, for certain things, I love it. I mean, it gets it right. Like when I have to do stuff down at the level of the hardware where I'm optimizing, for example, I want to pack something more efficiently using bit twiddling. Ugh, the LLMs know bit twiddling. I know the code that I want to write. It's just going to take me 10 minutes, but the LLM spits it out in 10 seconds, and I look at it and run a few tests and we're good. But that's programming in the small. For programming in the large, it's a whole different thing. And then the question is like, yeah, if you're not learning the foundations and the fundamentals, like, will you be able to tell that, this thing's introducing serious bugs, into your framework? So you might like say, oh yeah, it helped me build a web app and a new cloud backend, but actually it copied a whole bunch of security flaws, right? Because it doesn't maybe know the best security practices. Just it hasn't been trained enough, or it doesn't check its work. So yeah, I think we're at an interesting stage where there's definitely value to be gotten. For education, I'm a little worried because I do believe like we need to have some fundamentals so that we can make sense of what's going on in the world, and we can also make sense of what the AI is doing. Because now, I mean, the AI is very convincing acting like a human. And when we see that as humans, we sort of, because humans generally, like if they see something acting like the human, we project intent. We project a human brain there, right? And that's a very dangerous thing, I think. We have to understand that in the end, that's a program running on a computer. Yes, it was trained on a lot of data, but in essence, right now, I think we have to have a much more critical eye, especially in education, about what the limitations are, and also again about fact checking. It's like, do you trust this thing? Do you validate? And again, the role of testing and the role of sort of really foundations in terms of really understanding. Well, it's writing this Python code for me, but what does the Python code do? Big question. Lots of big questions.
You think usage of like hardware, like always going back to the hardware, always programming, flashing code onto a device, do you think that is sort of the continuous solution for like the education problem? As long as we keep grounding, as long as we keep reminding
Well,
ourselves of
yeah.
what the code is doing, then maybe people won't forget their fundamentals, let's say.
I mean, the underlying hardware will change. I think it's when we think about when I teach about the microbit, what am I teaching about? I'm teaching about reactivity. I'm teaching about the notion of computation and the notion of what memory is. So the microbit in physical computing helps students see, oh, this is a thing that can be embedded and, it can be programmed in. But at some point, I do think like you move up the stack to some abstractions where, you have a virtual machine, but you basically understand that that virtual machine, just like the hardware, has an instruction set, which is fixed, and there's a programming language for it. So I think there's lots of foundational things to learn. I do think for kids starting out, especially with arts and crafts and activities and wanting to run around, sitting kids in front of lab computers for long periods of time and expecting them to learn, at a certain age level is maybe we're training them the wrong way. So I do think like physical computing and sort of the microbit has its role. At some point, things get more complex, and yeah, we need to like talk about like the internet. I mean, kids need to learn about that, and they need to learn about passwords and security and privacy and all that sort of stuff. But yeah, I mean, I am of the mindset that, if I were to design like, curriculum in terms of like, and also thinking across subjects, yeah, I mean, I'm a bit of a Luddite that way. I feel like a lot of ed tech that goes in there into the classes is not really serving the purpose, is not helping the teacher. I mean, there's certain things obviously like that are great, maybe, maybe for grading and collecting assignments. I don't know. I'm not a teacher, but I do feel like there's a benefit to having, like with the microbit, sort of a more modular open system that allows people to discover. We're not like trying to sell like a solution into schools that's a monolith and sort of you have to just keep coming back to us. So I think there's also like in terms of what the BBC set up, we have sort of a very simple low cost device that can be used in many contexts and reused. So I think like rather than school systems, my vision of the future is like we should have maybe in place of the calculator, we should have sets of modules, hardware modules that we stick together and like we learn about computing as something that can be embedded and relevant to all different subjects. And we get to have a conversation about it. And we do it in a group because everything is local and we're not just connected to the internet to get the experience. So my view is like a lot of what schools do, like it's a safe sandbox for talking about concepts in the real world. And maybe it's not always safe, but it's safer, and part of my feeling about computing is like, yeah, disconnecting isn't necessarily a bad thing. We can still have computers in the classroom, but have the students work with them and not just connected to the internet, right? And watching videos. So I think there's a whole different way to think about how you introduce computers, which in some sense maybe is bottom up, but it doesn't mean we ignore the web browser. And that's what's cool about MakeCode. We like say, hey, look, if you have a laptop or desktop, we have this modern programming environment for this retro hardware, right? But one of the things we're doing actually is we're also thinking about, well, if I plug the microbit, and this comes back to touch develop, like if I plug my microbit into this, I've got a game machine. But why can't I program my microbit now? Why can't I put something on my microbit, which is a programming environment for the microbit? So we've actually done that. So again, I think like going away from these monoliths to sort of more of a modular solution that really gives power to the teachers and the students to sort of use the in different contexts.
Yeah, I think
that's a lot of philosophy, but that's sort of where my head is now.
What you said about like, kind of approaching this as like the calculator in the classrooms, I think is like brilliant, because I think like if we approached physical computing kind of the way that we approach like giving every student a calculator, like in grade school, for example, it would change the way that like it would advance probably the world of computer science much faster over a lot of time horizon. So I think that's like really a really good way of putting it.
Yeah, I mean, what I'd love to see like in the next, I don't know, before I truly retire, is like we see more of that vision, that the computing is sort of just it's a substrate or a foundation that the schools have that they can use in all their different contexts. They can use it in music, they can use it for environment, physics, and they can also teach programming with it, right? But for a lot of kids, it's maybe more to understand that the computer is used in all these different ways, but also that, you as somebody can adapt it. You can change it for different purposes. So yeah, so we're definitely also thinking about, um, what would it be? How would you work with the microbit if you didn't have an internet connected device? And so that's an
Yeah,
interesting.
I was gonna ask because I was curious if y'all are working on anything where maybe you build software for the teacher as well to maybe like monitor what the kids are like building in the classrooms. Because I'm
Yeah,
guessing to get like widespread adoption, you'd need some kind of like end-to-end system in the classroom, even if it's not like fully on the internet,
yeah.
right? And
So
just a way for the teacher to control that
yeah, yeah,
environment.
yeah.
Yeah.
So you should check out what's called the Microbit Classroom. So this is a very cool wrapper around MakeCode that the Microbit Education Foundation did. And what it allows the teacher to do is it allows the students, so it's a completely ad hoc way to network all the students in the classroom to the teacher using some local codes, but there's a cloud backend. And what it allows the teacher to do is to go from their device and see all the students' programs and to help them. And so yeah, classroom has been like a big deal because yeah, if you've got all these students in a computer lab and you want to sort of review their work, you have to walk around, you have to see that. So yeah, so this microbit classroom is a really cool uh, application made for the teachers to really help them deliver a microbit lesson, effectively.
One of the cool things about kind of all the work that you guys have done, I think, is that if you kind of like zoom out and see the bigger picture, it seems like the mission has been very much about accessibility. Obviously, with the microbit, you guys have expanded now. You have MakeCode, and you have all of these boards that can be used by the kids. And then additionally, so you've been doing some cool work on microcode. So could you explain microcode for someone and like why it's kind of like an important thing?
Right. So microcode is just one example of what we think of as apps for the microbit. So somebody else like me, a professional developer, creates an app for the microbit that then can make use of the display. And what microcode does is it takes a very simple visual programming paradigm that people might know as Scratch Junior, but essentially sort of left to right visual tiles, and it was also pioneered by something called Kodu Game Lab. But it's a very simple visual programming paradigm. So with microcode, you download this hex file on this binary onto the microbit, and now it's a programming environment and a runtime for the microbit. And so now with the screen, you can actually see your program and you can edit it. So think of it like Blockly, but super simplified. And also the APIs now are even simpler because there's no text entry and you have to do everything sort of with these icons. There are some tooltips and things like that, but essentially we designed microcode and then we evaluated it by looking at like all the beginning projects that the Microbit Education Foundation has for the microbit using MakeCode. And what we found was like we can do most of the introductory projects just fine with microcode. We can do like I think a third, half of the intermediate projects with microcode, and about a quarter of the advanced MakeCode projects for the microbit we can do with microcode. So what we've shown is that we have this ability now to take the microbit outside of the classroom to go to places that have no internet accessibility, as long as you've charged up, the battery for the shield, you're good to go. You've got essentially a little programming environment. Furthermore, when you unplug the microbit from the shield and you plug in a battery, the last program you created runs. So we also have the physical computing aspect, like it doesn't have to be attached to the shield to be functional. You can plug it into the shield to do your programming, you remove it, and you can you can still make a step counter, right? When it's plugged into the shield, you do the programming, you take it out. Kids love this. We've done some trials. We have a paper, user studies. Ownership, I think, well, first of all, familiarity. Like the kids get the visual interface really quickly. A lot of them have played games. It's like a Game Boy interface. But also, really, the portability is cool. Like we have a programming example where let's take the temperature at different parts in the school, right? And like you can run around with the shield and like do that, right? And it's much easier. Like you don't have to be you don't have to be connected, to the classroom. The other thing we've done is we've added graphing capabilities. So we have another app called Microdata, which is not programming. It's like using your microbit, and this is going to date me. I think of the Star Trek tricorder. So if you don't know what the tricorder was, the Enterprise crew beams down from the Enterprise in orbit around the planet to this alien environment, and Mr. Spock usually takes out this device and he scans the environment for signs of life or, toxins in the air. And so now, like, imagine, you put, the tricorder app on the microbit, and now, you have graphs of the temperature, you have sound. So again, one of the ideas, like, the microbit is very capable with the shield. So what can you do besides learning how to code? Well, the fact that it's portable means you could go out and take measurements, as long as it's not raining or you have some protecting. You can, and now with the shield, you can configure the app, you can set it to do recording, you can all these things that you needed previously, a laptop. You needed to take the microbit, connect it back to your laptop to see the data. Now you can do it remotely and portably. So that's super exciting. In some sense, we're sort of recreating the PC ecosystem in miniature. This is like your motherboard. This is your display and your keyboard, right? And then we have this other thing called Jack Deck, which is like we have like little cables, and you can connect more goodies and do more. So yeah, that's what's going on there.
Yeah, I love that. I think that's a really good way to put it. You guys are kind of like building the computer up from scratch, just like all these like small pieces interconnecting together. I'm curious from the user studies perspective. I don't know like how much of that stuff you can even talk about. I'm not sure if
Oh
it's
yeah, it's
public,
mostly
but
public.
yeah, so I guess what were some of the interesting insights that you guys got from the user studies from the kids? Like, was there anything that like surprised you about what the kids liked using the devices for, what they didn't like? What were like the main bottlenecks to like why a child would stop using the device or why a child would be kind of like willing to program?
Yeah, well, one of the things is this tiny small screen. Kids are used to big screens, right? So we actually have this tiny screen, and we actually and we've worked with hardware partners who've also seen this complaint, and so there is a larger screen model, and that's definitely one that is enjoyed much more, especially a lot of the projects the kids work in pairs, so the smaller screen is definitely difficult. So we've worked on supporting larger screens. But again, the microbit only has 128K of RAM. So, we're also thinking about future hardware SKUs where we might have more, or we put more RAM on the display shield or have some smarts there. Yeah, so that's all, in terms of the hardware, we've certainly gotten a lot of feedback. We also had, some manufacturers really, they like the microbit aesthetic of like the bare PCB. But then we find, things get dropped and things break. So we've definitely also seen like a lot of our manufacturers hardening their shields, like enclosing them, in shells. And so there's been just, the microbit by itself is pretty indestructible, very small. But once you get sort of bigger and you get the display, in terms of the programming, you really see like, I mean, one thing is like the kids really take ownership of like the device. They're like, oh, I'm programming and this is my shield. It's a little possessive, but on the other hand, they really sort of feel ownership about it, which I think is valuable. Of course, sharing is, always an issue. But in terms of like, in terms of some experience, we've definitely seen, that kids really like gravitated to it very quickly. In terms of the user interface, we've we really don't have to teach very much. There's, we let them explore, and it works quite well in terms of them, making progress and also retention. We see that when the kids come back a week later, they remember a lot about how to use it.
Are y'all planning on building any like networking capabilities into the devices? Because I know you said a big thing was collaboration like between kids, and I'm guessing that you don't want it to always just be on a singular device. You want them to like maybe be able to build a game and then play within like a local server or something.
Sure.
Yeah.
Yeah, so I mean, I mentioned before that the microbit itself has the Bluetooth antenna, and we make a lot of good use of the radio to do ad hoc networking. So one of the things we can do is we can put students into groups, and each group has their own set of communicating microbits. That is valuable for like a whole number of scenarios. Now, if we need more processing power, then yeah, what we can and what a lot of people have done is they use a microbit connected to a desktop or laptop as a gateway, right? So let's say we actually want to get some data from the internet and then have the microbit do something. So we've seen a lot of people do these projects where they use the radio to communicate across the microbits in the classroom, but then they have like a bespoke web app that talks to the microbit, generally the microbit connected, to the laptop desktop over serial, and then they do some then they have a bespoke app for getting whatever the data is. Yeah, so definitely, there's the microbit as a gateway using the radio for untethered communication to the other microbits, and then the microbit is essentially sort of on the internet, although it's not making an HTTP request itself.
Where do you see it kind of going kind of from here? Do you see you guys partnering, for example, with like really big hardware companies like NVIDIA, AMD, and then maybe, I don't know, you build out more feature sets, more software, maybe support the new robotics wave? I'm really curious what's going on that front.
Yeah, robotics is very interesting. I mean, if you look at, so there's a whole set of hardware partners for the microbit, and a number of them are just making very simple two-wheel cars, no stepper motors, just dead reckoning. There are some folks who are using more sophisticated robot chassis, with the microbit. And certainly there's a limit, to what you can do with just programming the microbit and controlling a complex system. So we do have, an amazing thing that's not robotics, but related, called the Microbit Orchestra, done by a fellow whose code name is Captain Incredible. And he's used the microbit and radio to do full drum kits and sequencers, and all coordinated over radios. The radio is highly deterministic and very, very much real time. So he's created like a whole set of instruments that are programmable via the microbit, and everything is microbit based, and that's very cool. So that one shows me that you can do real time. Of course, there it's much more one way. It's like you can program a sequence and then have the microbit sort of conductor send the beat out to everybody, and everybody plays their instruments. Now, what would be much more challenging, I guess, is to think about a robot control system like flying a drone or something. I know there is a microbit drone. I don't know how successful that's been in terms of flight. So yeah, I think the microbit's embeddable, connectable. There's lots of hardware out there. In terms of partnering with a bigger company, I don't know. Well, part of the microbit appeal is to keep the cost low. So like, with the microbit itself retails just by itself for $15 US. A lot of these simple robot cars aren't more than like $40. So yeah, I think there's also this question of like, we want to keep, for accessibility, we want to keep the cost fairly low. So I don't know how far we'll go. We'll have to see. Certainly, people have big ideas, and I'm prepared to be surprised.
Yeah, with that, I guess just bigger picture with the project itself, like what do you think the main sort of objective function kind of really is? Do you think it will be just keeping this minimalistic, cost-effective solution that ships out to people? Because even from a production standpoint, I'm curious, when you guys were initially making the microbit, was that kind of like the key thing that you were optimizing for, was just making sure that the costs of the actual device were low so that, obviously kids could play with it?
Well, yeah, keeping the cost low, but keeping the device capable. I think the microbit is at a sweet spot. Like if it didn't have Bluetooth radio, like one of the early prototypes, I think it'd be much less expandable. The radio, like we can program the microbit to send messages to the radio controlled car, and like we can program the microbit to be the controller. And so, yeah, so I think it's a sweet spot in the sense of like keeping the cost low, keeping, the set of things that are on board compelling enough to do initial projects, then having the extensibility through the edge connector, and then through what we did, with JackDAC. In terms of like, goals, I think the Microbit Educational Foundation has done a great job since the last 10 years. There are over 10 million microbits that have been distributed, bought essentially, or, in some cases, there are philanthropic efforts. So 10 million distributed worldwide, over 60 countries. But I think, there's still a lot of people who don't I don't think the accessibility is 100%. I mean, I think it's still primarily to places that have decent internet connection and computer labs. So personally, I'm looking at this as something where we have a beachhead, which is great. We have a stack of hardware and software. We have hardware partners, but there's still like a lot of unaddressed audiences. So one is remote, maybe rural, not, no internet, poor internet connectivity or lacking computer labs. A second would be, the microbit again, is with MakeCode was really targeted at middle school, but can we expand the applicability of the microbit to more age ranges? So microcode is an example where we try to make it easier for younger kids. Yeah, and then, I think there's also this, what I mentioned before, sort of this notion of really using modular computing across subjects, right? And so this idea of the future calculator, like what would it mean to have a school system that had, the microbit and these modular kits and apps that were repurposable and reusable? Because I don't see that today, right? I mean, what I see today is I see, the triumph of consumer devices that have basically been embedded in education, right? They weren't designed sort of with educators or iterating with educators heavily. I mean, and we can think some of them maybe, but for the most part, I think we've seen like the real success of consumer devices, in education with pros and cons, and so I think there's the bigger picture is this other way to think about computing, which is more about people constructing the solutions themselves rather than having them handed down. And even if they've been given an app, like say microcode or microdata, it's actually open source, it's editable, and it's like created in a way that encourages people to modify it, right? Which is not true of things in the app stores.
Yeah, I think it's brilliant what you said about like modern education relying on like the personal compute that we use today, because yeah, even in like the smaller classrooms from like pre-K up until like 5th grade, 6th grade, like they're using laptops now, and like these expensive laptops, right? I remember in my I was in this Ascend program in like middle school, and I remember we had this like rack full of like MacBook Pros or MacBook like Airs or something like that. And so yeah, I mean,
Right.
but that's because we're in like the American education system.
Yeah,
right?
exactly.
And like we are extremely privileged in a sense. And so I think that is what's like incredible about what y'all are doing, because you're kind of trying to like bridge the gap, right? There's so much global disparity in terms of education.
Yeah,
and I
exactly.
think that's crazy.
Yeah, I mean, I think there are other paths to explore, and this one is, I mean, yeah, we'll see where this ends. I don't know, but those are some of the goals. I think increase accessibility, think about cross subject, and really also think about. I mean, it'd be wonderful if everybody's connected, I suppose, but I don't think that's the reality we're in. And even if they're not, I think there's still in my mind this sweet spot, which is like computing in the classroom that's disconnected from the internet, right? Like, I mean, there was there's a set of projects around computing without a computer. I can't remember the name of it now. But again, you can start to learn about ideas of computation without computers. But then why do you have to jump immediately to an internet connected computer? There's so much you can learn sort of with computing technology if it's designed in a way that makes it sort of modular, compositional, and also discoverable and editable. And so I do think that's what we're after in the larger scope.
What things have y'all found like with global education disparity? Like is there kind of like actual evidence that you guys have found in specific maybe countries or places that you guys are targeting? Or I'm really curious about like what your insights on.
Yeah, for that, I think it's difficult. I mean, I'm a tech guy in Microsoft, so like, we work with partners who are at the front line. So I've worked with some nonprofits, you know, who work like, for example, in rural Canada, where you have, it's a flight just to get there, and then a boat ride, and then you get there, and the connectivity is very sporadic, right? So there's definitely places where the kids just don't have the sort of resourcing we have. But yeah, I can't. Yeah, I mean, I wish I had stories to tell directly. I mean, part of my goal is to work more closely with those orgs and to learn with them. But even like Washington State, like east of the Cascades, rural communities, I know there's, when I've talked with teachers and researchers here, there's needs there as well. So I'm probably going to start out closer to home. But yeah, it's a very good question. I wish I had more to say on that.
One of the things that I think is interesting, I don't have the exact numbers pulled up, but I think if you've tracked literacy in the United States, even just in the education system that we have today, I think people are doing worse and worse on both math and reading kind of
Mm,
universally across the board. And
yeah.
even just kind of on a sort of an anecdotal sense, like the sense that I've been seeing on like Reddit and like other public forums is that
Mm,
it seems like students aren't engaging as much with like college education in general. Like I think it's a
yeah.
very all these consumer products that have been deeply embedded into education, but also just like outside of education, obviously, like just on a daily use. It seems like it's having a profound effect on attention and just how people
Yeah.
are engaging with
Yeah.
material. How do
Yeah.
you think we solve that? I mean, it seems like obviously you guys have an interesting paradigm of building things up from the bottom up. Do you think that's like we need to start reinventing education to adopt that approach, or do you think it's something kind of deeper?
Well, I mean, we also had COVID, which is a huge change for so many people, and we're still feeling the effects of that. I think a lot of learning takes place face to face with other humans and struggling with projects that fail and don't work. And um, I think I mean, we know about things that work, but we also, we have this. I mean, we have, the computing has been so successful. We have these cheap supercomputers in all our pockets. So yeah, I mean, I think in some sense we do need to rethink about what we're asking of students. I don't know. There's I know there's a lot of raging debate now about like, well, should students give up their phones when they enter the school system, right? I mean, like, and I've heard both sides, and I don't really know. I mean, I'm sort of siding with, well, the way I learned was blah, 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 and it was good enough for me. But that's not reality. That's not what we're in today. So, what's a really good rationale for having phones as part of classroom education? And with Touch Develop, we sort of had an answer. Well, it's like you can actually program with the thing. So we were like, you could learn to code with it. But I yeah, we will see. It's a sort of very interesting debate. It's like what we have this very powerful and seductive technology. I mean, we certainly. I mean, these analogies aren't great, but I always think like you learn physics, you learn a lot about how the physical world works, and you work your way up, and eventually like you can learn to drive a car. But before that, you've learned about the frailty of the human body, you've learned about physics, you've learned about what it would mean for a piano to fall on your head. Maybe you don't really need to learn that, but I sort of feel like before you get behind the wheel of a car, you've learned various things about how the world works. And I'm not saying that makes everybody into a good driver, but you wouldn't like say, "Hey everybody, we've got cars today," to the third graders. Let's see what we can do with them. I mean, it's a bad analogy, I know, but it's sort of like just because you have the tech doesn't mean you should just bring it into the classroom, right? And I mean, obviously, we don't bring cars in. We don't like have them in the playgrounds to play with either, because we don't want kids getting killed. But you know, we have to think seriously about what the benefit of this tech is. And again, I'm not an education researcher, so I can't really speak to it, but I do feel like we're out of balance. I think things have tipped like too far in one direction. So I'm at least hoping to counterbalance, but I don't know where we're going to end up. It's a big mystery to me. I'm
Yeah,
afraid.
I mean, yeah, kind of just like kind of adding to the conversation. I was talking to Laith about this quote that Yan LeCun said recently, where he was saying that inventing new things requires a type of skill and ability today that you're not going to basically get from large language models and all these other like resources that we have available to us. And I think kind of I want to get your insights on this, just kind of like open conversation, but I think what's really interesting is that kind of what microbit is doing outside of just first principle thinking is you're teaching kids to be curious and invent new things, and maybe that itself is like a skill that's necessary to kind of like fix the education system, because in a sense
Yeah.
the education system doesn't really push for curiosity and invention. Kind of pushes for like learning as much information in a short span of time as
Teaching to the
possible.
test is
Yeah, teaching to the
um,
test and things like that. So,
yeah,
kind of, I'd love
yeah.
for you to kind of give your
Yeah, the
insights on that.
microbit comes out of sort of, constructionism, that the idea that you, by building things and exploring, you learn and you gain knowledge. And so very much like, there's educational theory and there's like various approaches where, the microbit sort of fits into, as with Scratch, a lot of the work of Papert and others, that you had the Lego turtle, and you have many, many examples of this. The microbit is definitely very much in that tradition of sort of project-based learning, of also like making room for creativity. So like, why do we call the thing make code? It's because, well, the first thing is you want to make something. Well, what do you want to make? Oh, I want to make a robot, or I want to make an art project with animation, animatronics, and really the coding is second. It's make code. And you want to make something. What is it you want to make? The creativity. And then the coding is also creative, but there's a set of rules you need to follow for the program to work. So I do think this notion of project-based learning, of encouraging exploration, but also incorporating the students' interests. Some students might be really into storytelling. They could use the microbit for that. Others might be super super interested in animation, or others might be in music. And so, again, this is sort of like the cross curricular aspect, is, or cross subject, is like, can you have like a palette of different types of things that you can do, that also, when you have a set of kids and you're working together, you might have certain things you want them to learn, but in terms of like maybe learning objectives around computing, or maybe you want to learn about variables or things, and you might give them like a little lesson and do one project, but then like let them explore, like what else can you do, and sort of, so that sort of project based learning, I think, is definitely also a bit of a antidote. But there's always a question, like, we want to evaluate the kids, so what have they learned? So you also have to really have some notion of a pedagogy, but within that, I think you can be quite flexible. That's my hope. But another issue is, of course, like giving teachers the confidence that they can work with the technology. So even today, I mean, teacher training is a huge, huge issue. That was a big part of what I learned about working with the microbit, is like, how are you going to train all these teachers to work with the microbit so that they can work with the students? And teachers are so under stress with so many classes to teach, and just sort of, how do you find the time to learn these new things? Well, one thing that we think is, like, you should make it easy. Like, you should reduce barriers to friction, and also have great content. And so, there's a whole, I mean, what I do find interesting about the whole project that the BBC did was, it really introduced me to, what it really takes to do something end to end. It's not just about having great tech and a great programming environment. Oh, you need content too. Oh, then you need, professional development, teacher training, and all of that. This is like also why, I partner with a lot of different types of people, because to really make headway on it, you need diverse thinking from a number of different perspectives.
And kind of on the same thread of working on projects, I'm curious, from an engineering perspective, you guys had a lot of variables to optimize for on all these projects. So, as someone kind of like leading those engineering efforts, what does it take? Like, how do you organize the team in such a way where you guys are able to ship, like, I mean, even microcode, for example, getting something like that to run on the device,
Yeah.
getting the compiler into the web app, these kind of ambitious, lofty goals that have to get done, even in a timely manner when you guys were doing the BBC program. What was
Yeah.
the
Well, I mean,
engineering leadership like for that?
well, I don't know about my leadership, but I tell you, Miha Moskal and Pele Dehalu are our principal software developers, and they did a huge amount of that leading because they've built so many different types of systems. So I have to give them the majority of the credit there. In terms of like, making progress, again, it's a team effort. We have Lancaster University. They do the C++ runtime for the microbit, and they also deserve a huge amount of credit. That runtime has actually been generalized, so it is it is the basis of sort of all the MakeCode devices, and that has been a multi-year effort on their part, and we continue to work with them. So yeah, then we have the firmware. Lancaster University does that. Then, like the MakeCode team, they don't do so much on the hardware side. That really came out of Microsoft Research in Lancaster. But they're full stack web devs who are very good at what they do. And the part of what they're doing is like every year they're doing a new release of MakeCode for the three editors. And through that, there's always continued improvement and feedback. I am not in any way leading the architecture engineering of MakeCode anymore. I mean, for microcode, what we're doing, what I have worked on is really thinking about the MakeCode tool chain now as something that is available to a professional developer or somebody who wants to create an app like microcode or microdata. So one of the things we're doing is we're starting to build a community around these microbit apps, and we are creating a set of resources and new libraries with the help of the MakeCode team. So for example, a professional developer is very happy in VS Code. So we have a VS Code integration of MakeCode along with the simulator. So now, anybody who's a professional developer on GitHub and used to VS Code, boom, they're just happy right away. They don't have to try to code in this wonky web app that was created for education purposes. So yeah, so that's where I'm spending more of my time now, is really thinking about, if we're going to be successful in this world where we don't always have MakeCode, how are we going to create like the next generation of infrastructure for people to create these types of apps.
Yeah, and I mean, just kind of like getting near the end here, we noticed like kind of the two things you're kind of mainly working on based on your LinkedIn and other things that we researched was device script and the Jack deck. And I'd love for you to just kind of dig into those, and why is it that we've kind of converged here after everything that you've kind of done in your.
Yeah, so device script is actually really not an active project. We did that as a way to sort of think about pivoting from the things we did with MakeCode and JavaScript for devices to more of a professional developer experience. And it's pretty cool, but I have to say there's like, for anybody who wants to program embedded, like for serious professionals, there's a lot of competition out there. So device script was actually something that spun off of this JackDack project, but I won't talk much more about it. I mean, I would like to say it's active. JackDack is super active. So what is JackDack? So JackDack is the idea, well, the microbit or any device has some existing set of sensors, but how would you extend it? And actually, I can show you here. So we have this PCB, and we have this connector on it. That's not a microbit, but we designed this connector, which is part of the PCB. We also have a way to connect. So sort of like USB, like plug and play. Like, so the idea of JackDack is, let's take the idea of the microbit, but let's make it compositional. Let's allow you to add to the microbit. Let's say you don't have the cool RGB color LEDs that you have on the round board, the circuit playground, but you want to add some. How can you make that like a plug and play experience? So we want to keep things low cost. USB is too complex essentially for the price point we're after. So we designed like a new cable, a new protocol, and we essentially have a set of manufacturers who make these JackDack modules. I don't know that I have one. I don't think I have any handy right now. But these JackDack modules are things that are like input devices, like sliders, more buttons. Let's say you want to make a kiosk, right? And you want to make a kiosk that has like a set of buttons and sliders and also a screen. Well, the microbit just can't do all that. So With JackDack, you can attach the microbit into a holder, and then you can start adding all these other devices, like all these other peripherals. And essentially, JackDack has a protocol in addition to the hardware that makes these modules or peripherals discoverable, and it also integrates with MakeCode. So in addition to the microbit simulator, we have simulators for all the JackDack devices. So one of the things we discovered when we're doing MakeCode, yeah, people want to add hardware all the time. So you slot, the microbit into a piece of hardware, and how do you use that hardware? Well, you have to add a library. But when you add that library, the simulator remains the same. Like, it doesn't show you the simulator. So now you're in a state where the microbit can be simulated, but the hardware can't. So with JackDack, we wanted to do a number of things. We wanted to be an extensible system where you can add stuff, but we also wanted it to have all the goodness of the microbit. Low cost, reliable, and also for everything you add, you have a simulator. So if you don't have the hardware, you can play with the simulators. And so that's what we've done with JackDack. We've made a modular system that can extend not just the microbit, but other types of computing, microcontroller-based computing. And so JackDack, actually, we have 1, 2, 3. It was slow getting going, but we have like 4 manufacturers of devices. We have a company that's actually built a whole product around the microbit, MakeCode, and JackDack called Forward Education in Canada. It's very exciting, and they have a kit that's out already, and they have continuing plans around JackDack. So yeah.
So, kind of to summarize, because I think we've gone through a lot, especially this suite of products, I think the common theme has definitely been about making education and engineering more accessible and something that kids can enjoy. So I guess with this accessibility, with these devices that are out there on the market, hopefully low cost and everything's kind of available for everyone. For someone who's, either like raising a kid or maybe they're someone who's like in their education, midway through their education, why should they learn to code? Why should they learn to program hardware devices? Why should they learn to program?
Yeah, I think that it's about having enough understanding about how systems are built. It's not necessarily about having a career as a coder. It's more to peel back the veneer or the surface and to understand, like, there are computers everywhere. They're programmed by people, and there are various constraints around how these things work, how they're programmed, what they're capable of. So I think it's not about learning to be like a proficient professional programmer. It's to understand it's to understand enough to sort of be knowledgeable to ask questions, to be critical, to be a critical thinker, to not just say, oh, this is like a cool device that I can do all these things with, but to understand a little bit about, say, the physics behind the computing, just like we try to understand about fire and water and wind and energy and all these things that help drive our economy. Well, computing is, and the world, all these other but the computing, I think, is very abstract. I mean, it's hidden, it's well hidden away, is what I should say. So I do think it's important to get an idea of maybe the concepts of computation and algorithms. People talk about computational thinking. Learning to program, yeah, for some, I mean, it's going to be really cool. Maybe everybody will be able to program in the future with natural language. We'll see. Like in Star Trek, we'll just talk to the computer and say, make it so. But I do think we need to have a little bit of understanding of the underlying basis of how computers work, the idea of processing, of memory, of computation, of networking, because these basic foundations aren't going to go away. We're always going to have computing, networking, storage, and then all the applications that are built using those. If we want kids to be better stewards of their private information, they need to understand a little bit about, what cloud-based storage is. And, so it's to me, it's more about the concepts that are, I mean, programming languages come and go, right? But like the basic components of computation and modern computing, while we think they change really fast, actually there's a lot of the foundations that stay the same. So, and I don't know that we're really teaching those. So I'm hoping with the physical computing we can get into that. For example, like with the microbit, it's super fun. You get a little radio program where you send messages back and forth, and then it turns out everybody's on the same channel. And then you like very quickly start to talk about security because people can snoop on each other. They can like send messages to each other. And then you talk about, well, how would we keep the microbits from sharing too much information, right? So I think like there's a whole set of, to me, that's not about programming. We introduced some programming to talk about a really critical concept, which is communication and networking and privacy, right? And that can like lead to like a whole lot of learning. So yeah. I mean, learning to program again with the age of AI, I think it's going to be important for a lot, and certainly, but for everyone, I'm not. Yeah, I'm not.
Well, Tom, thank you so much for coming on the podcast. I think you've given us a whole lot of information to go home with. Hopefully, we make education much, much better than it already is.
Yeah, I hope so. I thank you so much for giving me the time and the opportunity. Really appreciate you digging into my background and the projects that I've worked on. And yeah, best of luck to you in the podcast.